In magnetic resonance imaging, or MRI, detailed images of anatomical structure are produced using strong magnetic fields. The main magnetic field of a modern scanner is at least 30,000 times the strength of the Earth's magnetic field. The images obtained by MRI are made possible by the physical properties of certain atoms in strong magnetic fields. For example, each positively charged proton in a hydrogen atom rotates around its axis, creating a tiny electrical current. In a magnetic field, this current induces a torque called the magnetic moment. The arrow indicates the orientation of the field. Because a hydrogen atom has an odd-numbered atomic mass, its spin results in an angular momentum. Both a magnetic moment and angular momentum are required for nuclear magnetic resonance, or NMR. When no external magnetic field is present, protons in the brain are oriented in a random manner and together have a net magnetization of 0. When a strong external magnetic field is applied from the main magnet of the MRI scanner, the protons line up either parallel or anti-parallel to the applied field. Slightly more than half of the protons will line up parallel to the applied field, a lower energy state, creating a small but detectable net magnetization of the tissue, abbreviated M. The protons do not line up precisely with the axis of the applied magnetic field, but actually precess or wobble a few degrees off the central axis in a manner analogous to a spinning top. Spinning objects respond to applied forces by moving their axes perpendicular to the applied force. Within a strong magnetic field, the nuclei will precess around an axis that is either parallel to the magnetic field, low energy, or anti-parallel to the magnetic field, high energy. If energy in the form of radio waves is applied at a particular frequency, some low-energy spins will absorb that energy and change to the high-energy state. After this excitation energy source is removed, some spins will return to the low-energy state by giving off that energy over a short time interval, the reception period. This energy release is in the form of electromagnetic energy that can be detected by the radio frequency coils of the MR scanner. Measurement of this emitted energy provides the data that go into our images. Functional MRI, or fMRI, is a variation of MRI that, like PET, provides information about brain activity. fMRI is based on the fact that oxyhemoglobin, the oxygen-carrying form of hemoglobin, has a different magnetic resonance signal than deoxyhemoglobin, the oxygen-depleted form of hemoglobin, or the surrounding brain tissue. Brain areas activated by a specific task utilize more oxygen. Initially, this activity decreases the levels of oxyhemoglobin and increases levels of deoxyhemoglobin. Within seconds, however, the brain microvasculature responds to this local oxygen depletion by increasing the flow of oxygen-rich blood to the active area, flushing away the deoxyhemoglobin. Oxyhemoglobin is diamagnetic and does not affect the magnetic field. However, deoxyhemoglobin is paramagnetic, and changes in the total amount of deoxyhemoglobin will affect the MR signal. These localized blood oxygenation level dependent or bold changes thus provide a contrast mechanism for detecting neuronal activity with fMRI. By having experimental subjects perform different types of cognitive tasks, the selective activation of particular brain regions can be identified. fMRI thus makes possible functional neuroimaging studies that seek to map different mental processes to different parts of the brain.